कीमतें लगातार आसमान छू रही है और हर रोज एक नया रिकॉर्ड भी बना रही है। अंतर्राष्ट्रीय बाजारों से लेकर भारत के घरेलू मार्केट तक में सोना बहुत से बहुत ज्यादा दूर होता जा रहा है।
Today, it's gold that is shining the brightest. Gold is glittering like never before on the MCX. We've seen prices have hit a fresh all-time high level of 1,06,000 rupees per 10 grams.
पिछले दिनों ट्रम्प टैरिफ के बाद सोने के भाव तेजी से बढ़े और गोल्ड की कीमत 1,04,000 को पार कर गई।
Gold prices surged to historic highs on Indian exchanges. Gold and silver prices are trending higher in India.
Welcome to Smart India Hackathon 2025. We are Team Auric based tackling problem IDSI H25056. As we know that gold price is increasing day by day, therefore using destructive method like fire assay method is a direct means of loss of gold, which means it causes loss to the customers, jewelers and to the economy. That's why it's very much essential to adopt a method called non-destructive testing method. As we know, gold fire assay method is most accurate, but it still needs cutting or drilling of jewelry which damages the article. And even it releases harmful emissions like nitrous fumes or lead oxides, which cause harmful and which is harmful for the environment. Therefore, our solution proposes a multimodal characterization system which comprises a dual X-ray imaging, terahertz sensing, spark OES, and nuclear based analysis for gold determination even in a accurate way like same as fire assay method. So our lab scale prototype comprises of non-destructive testing methods like dual X-ray imaging, which provides a detailed imaging of the gold items allowing visualization of internal structures, density variation and plating thickness. It can differentiate between pure gold alloys and base metals hidden beneath the thin plating, making it highly effective for detecting counterfeit or hollow structure. Second method is spark optical emission spectroscopy, which uses a high energy electrical discharge to excite atoms or the surface on a sample, producing light that is analyzed determining its elemental composition. This method delivers precise alloys characterization, identifying trace elements and impurities in bulk gold. So the third method is PGNAA, which is a nuclear based method used for the sample bombardment with neutrons producing prompt gamma rays unique to each element, which enables accurate qualification of bulk gold content even in large or heterogeneous sample, making it suitable for mining and hallmarking applications. Fourth step is advanced terahertz sensing, which uses terahertz radiations to probe subsurface layers and detect structural irregularities. It is highly sensitive to voids, cracks and multi-layer coating, enabling identification of concealed base metals or hidden cavities within jewelry and coins without causing damage. And our portable prototype consists of methods like Raman spectroscopy, which shines laser on jewelry and analyzes the scattered light to identify surface chemistry. It is useful for detecting coatings, plating and verifying surface label composition without damaging the item. Next is handheld visible spectrometer, which measures how visible an infrared light reflects from gold and alloys. Different alloys and impurities give distinct reflectance pattern, helping in quick field analysis and authenticity. Our prototype consists of AI and smart imaging, which combines the data from all the sensors using AI-based algorithms and smart imaging.
Of concept, we have designed a small prototype that demonstrates the principle of non-destructive testing and discrimination of gold from other metals or golden colored items. While this model is not a final industrial solution, it shows how different sensors can be integrated for layered testing and decision making. Our setup complies with the philosophy of BIS IS 1417 2010 for gold articles and aligns with ISO 9201 2019 principles for non-destructive. Now let us explain the sensor used. Here we have used the TCRT 5000 infrared sensor. which works on the principle of infrared reflectance. It emits infrared light and measures how much of that light is reflected back from the surface, giving us an indication of the material's reflective properties and texture. This helps in differentiating between surfaces based on how they interact with infrared light. Alongside it, we have used the TCS 320 color sensor, which captures the RGB values of the surface under test. This sensor detects the surface color profile of an item. It helps us to show that color alone cannot be trusted for gold identification. By integrating both sensors together in this frame, we demonstrate how reflectance and color data can be combined to provide a more reliable basis for material verification, reducing the chances of misclassification. CSR-0 for ultrasonic sensor. This ultrasonic sensor measures distance and positioning, ensuring the item is properly placed and aligned for consistent testing. In larger application, this principle is also used for thickness and dimension checking. Here we have used a load cell with an HX711 amplifier. This sensor measures even small changes in weight with 90 servo motor. The servo is used here for controlled positioning and scanning. In proof of concept, we have designed a small prototype that demonstrates the principle of non-destructive testing and discrimination of gold from other metals or golden colored items. In this demonstration video, we placed different samples. At first, we placed a regular coin which is not gold. The system identifies it as not gold. Then we placed a golden colored coin which is plated but not real gold. Again, the color sensor detects yellow, but the system rejects it as not authentic and displays it as not gold detected. Then we placed a silver bangle. The system detected it as silver like due to different reflectance and density characteristics. Again, the system rejects it and displays gold not detected. Finally, a real gold ring. The readings are consistent with genuine gold and the display shows it as detected. This proof of concept highlights an important point that our solution does not just rely on surface color but integrates multiple sensor readings to minimize false positives. This proof of concept highlights an important point that our solution not just only rely on surface color but integrates multiple sensor readings to minimize false positives. In future scaling, we will replace these basic sensors with advanced industrial grade in techniques such as Raman spectroscopy, dual X-ray tomography, conductivity mapping and spark OES, which forms the foundation of our two-tier model, a portable model for jewelers and small shops and a lab scale system for hallmarking centers and mines, ensuring accuracy at every level. What makes our approach stand out is its compliance with IS 1417 2010, ISO 9201 2019 and other hallmarking standards, ensuring reliability, auditability and global acceptance. Our prototype represents an initial but significant step toward the future of gold assaying in India, and we look forward to advancing its potential through the Smart India Hackathon 2025.